Hello, dear colleagues. My name is Oksana Pichugina, and today I'm presenting our paper, MoFlow, a graph theoretic algorithm for by-criteria allocation in intelligent and AI-driven systems, prepared in collaboration with my colleagues. We study how to allocate system components while combining high efficiency with low security risk. The presentation has 4 parts: the problem statement, our solution technique, a numerical example, and conclusions. We introduce the method of ordering fractional linear objective on permutation MoFlow. Each solution is a permutation representing a complete assignment of components to operational slots. We consider 2 conflicting goals: maximizing performance efficiency and minimizing the adversarial security risk. The first criterion, F1, is the performance output relative to resource cost. The second, F2, is attack exposure relative to protection cost, and it is minimized. A key concept is operational slot, which is a functional position in the system pipeline, network, or hierarchy. Each slot has 4 parameters: performance output, resource cost, vulnerability, and protection cost. We assume that the number of components and slots is n. A permutation x describes the full assignment, where component xi is placed in a slot I. As a result, the feasible set contains n factorial assignment associated with vertices of the permutational polytope. The following coefficient vector describes the system: C, performance; D, resource cost; A, vulnerability; B, protection cost. The regular coefficient structure, arithmetic structure, allows comparison of neighboring assignment by analyzing simple minors of order 2. F1 is evaluated as a performance divided by resource cost. Respectively, F2 is the total attack exposure divided by the total protection cost. We aim F1 to be maximized and F2 to be as low as possible. For computation, we use threshold rho star, which is maximal tolerable risk to protection ratio. We maximize F1 while requiring F2 to be at most rho star. By varying this threshold, we obtain Pareto optimal solution of the initial problem. Now, let's move to the solution technique. MoFlow exploits the above coefficient structure along with the geometry of permutation and aims to order assignment by F1 without directly evaluating or sorting every candidate. The method has 3 phases. Phase 1, reduction. The minor of order 2 determine how F1 changes between neighboring permutations. Phase 2, structuring. Signs of the minors or and permutation graph arcs built recursively from G2 to Gn. Phase 3 is identification. We traverse a Hamiltonian path HP and stop at the first assignment, satisfying the security threshold constraint. MoFlow algorithm. First, the performance and security minors are computed. Next, the graph and ordered HP are constructed. Finally, we check F2 along the path. Since the path is ordered by decreasing F1, the first feasible vertex is Pareto optimal solution of the allocation problem corresponding to the selected threshold. Consider as example, consider 4 components: a pipeline sensor, edge processor, a communication gateway, and central inference engine. The task is to assign them to 4 slots with different universal exposure. The key point is a conflict between best performance assignment and safest one. In phase 1, all performance minor are computed and they are positive. Therefore, the source of HP is 4321. The security minors are computed in the same way and confirms conflict, Pareto conflict. We built a graph G4 on 24 vertices. Its Hamiltonian path orders the assignment by F1. Then we can test condition that F2 is at most 1.64, and all results are here. The table shows selected checkpoints. The first 13 assignments violates the threshold constraints. The first feasible assignment is number 14, which is 1432, and it is a Pareto optimal solution where F1 is equal to 2.3846 and F2 equal to 1.3111, which is less than this threshold. In practice, the central inference engine is placed in slot 2 rather than more vulnerable slot 1. Additional checking of all permutation confirms the result. In conclusion, we formulated component allocation as a bicriterial problem, as a bicriterial fractional linear optimization problem on permutation, and proposed the method MoFlow for its solution. The method combines exploring specific matrix minors, a permutation graph, a Hamiltonian path traversal with a security filter. Applications include critical infrastructure, intelligent healthcare systems, adversarial AI defense, civil protection, etc. In future, we plan to extend the study to lazy path generation, repeated components types, uncertain coefficient, multi-level security thresholds, and computational benchmarking. The main theoretic and the multi-objective optimization sources used in this study are shown in the slide. Thank you very much for your attention.